This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening and welcome to the Jeffrey B. Graham Perspectives on Ocean Science Speaker Series. My name is Cheryl Peach, and it's a great pleasure and a privilege to introduce our speaker this evening, Dr. Devendra Lal. Dr. Lal, besides being just a wonderful man, is a nuclear geophysicist here at Scripps. And I don't know how many of you guys know it, but he really is a world-renowned scientist. He's really one of the most prominent scientists here at the institution. Oh, I see somebody in the back that does know that. It appears that Dr. Lal has a fan club here in the audience. His primary area of research is actually in cosmic ray physics, nuclear physics, earth and planetary sciences, and astrophysics, and he's made fine contributions in all of those fields. And I don't want to spend a long time talking about his history as an academic, but I was very impressed in looking back at Dr. Lal's history to see that he is a distinguished fellow of no fewer than 16 prominent organizations, among them the Royal Society of London, the US National Academy of Sciences, and the Indian Academy of Sciences. Then when you look at his awards, they're equally as numerous, and without listing those, I'll say they culminated in a medal that I'm very familiar with in the field of geochemistry, the Goldsmith Medal. So suffice it to say that Dr. Lal has made numerous wonderful contributions to the science, and we're really fortunate to have him here speaking on his research. Now, I really, I hope I don't embarrass you, Dr. Lal, but he also is a supporter of graduate education, excellence in graduate education. And he is the founder of a fellowship endowment for graduate students at Scripps in the fields of nuclear and isotope geochemistry and geophysics, chemical oceanography, glaciology, and climatology. So I applaud his dedication to supporting the next generation of scientists here at the institution. So please join me in welcoming Dr. Lal in his talk, Direct Measurement of Solar Activity in the Past 35,000 Years. Thank you so much for being here. Thank you so much.
Distinguished ladies and gentlemen, I am very honored to have been invited to give this talk. I will be talking to you about solar activity in the last 35,000 years. So let us begin by a very brief outline of the talk. We will discuss why we should study solar activity, because I don't want to load on you something which you may not be interested in, which may not be useful, but I want to promise to you that the solar activity is a very important parameter because it is related to climates. And how is solar activity studied at present? And this record goes back to, the good record of solar activity goes back to only about less than 300 years. But it is the record of climate goes back to millions of years. So if we have to understand what controls the climate, then we should be able to measure the solar activity in the past. And that's the reason why this work has been done. So we will discuss with you the new method, how we study the solar activity in the past. And then we'll discuss the question whether the new method gives more quantitative information on the solar activity, or it is not as good as the method which has been used so far. And then the last question is how far back in time. So this, the title says 35,000 years, but we will discuss how far back in time we can go. So as we all know, sun is of course the principal source of incident energy on the earth. And the internal heat of the earth is a very minor component. So the main energy source is the sun. And therefore it has been generally assumed that Earth's climate, its winds and hurricanes and the ice ages and the warm climates in the past, they are all as a result, they are all happened as a result of the solar energy which is incident on the Earth. But this question has now been debated because we don't understand the variation in the solar energy is so small, as we will just see. When we measure the solar energy during a 11-year cycle, which is the prominent cycle of the sun, we find that the climate forcing is only 0.2 watts per square meter, which is actually corresponds to less than 0.2% of the total flux. So here is the paradox. One asks the question, how can such small changes in the solar flux cause ice ages, warm periods in the past? So this has been a very big problem, and I want to show you the direct measurements of the solar energy which have been made. Here, I hope everybody can see this. Some of them may not be very visible. So these are 6 different methods of measuring the solar activity in different frequency ranges. Now, please note the y-axis, the amount of flux is only is about 1370 or 1372 or something like this. But you can see the variations are only plus minus 1. So the total energy which comes in, on that, the variation only plus minus 1 or plus minus 2 out of 1350. So this is extremely small variation, and these measurements have been done extremely carefully, and they are very precise. The measurement at the bottom, the measurement here refers to the visible energy which is coming from the sun. And you can see again, the unit is 1366, 137, but the variation is only plus minus 1. So out of 1370, only the variation is plus minus 1. So the big problem is how come this can cause ice ages. So we are going to talk about solar activity. Now this doesn't refer to the solar flux. I am not measuring the solar flux. It is an index of solar plasma and magnetic flux, as I will discuss in some detail. For example, during 1400 to 1800 AD, there were several periods of very low solar activity. This is the period when immediately after the medieval warm period, there was a cold period which was designated as Little Ice Age, which is very commonly discussed. And you can see this here in the next figure. So this is the medieval warm period. This is the temperature anomaly. And this is the Little Ice Age here. And this is the time when there were several periods of very low solar activity. So there is a hope. It seems to say that maybe the solar activity in some way is responsible for the cold climates. You see, what happens is on the Earth, oceans store a lot of energy. Now, if you can disturb the oceans, although this solar energy which we talked about before is constant, but if somehow or other you can disturb the oceans, then large climatic changes can take place because sun stores energy in the oceans. So now the question is, what does it? Now still we are not clear about this, and at the end of the talk also we will not be clear how sun manages to bring ice ages and warm periods in the last millions of years, which we have seen several times, which has happened. But we notice here that we had a little ice age during a period when there were several cold, very low periods of solar activity. So it seemed important to study how solar activity changed in the past. And I want to repeat one thing. We have very good climatic record in the past, going back to millions of years. So if we can somehow or other measure the solar activity back to millions of years, then we can correlate the two and find out how much effect of solar activity is there on climate. So first let me tell you how is solar activity measured today. Conventionally, solar activity is measured by measuring the sunspots. I do not know whether any of you have seen the sunspots directly. When the sun is setting, when the sun is very reduced light emission, at that time you can see sunspots, but as I will tell you, this is, please be very careful in looking at the sun. It's not an easy thing, but there are sunspots. Let me show you. This is a picture of the solar disk where there are sunspots, and please note that some are very small sunspots, some are big sunspots, and there is a reason why I am telling you. I will come to this a little later. But the most important thing which I want to emphasize, and I don't want to give you the wrong impression that you can look at the sun and look at the dark spots. Solar light is tremendous. It can burn the eye. So unless you have very dark filters, please do not attempt to look at the sun. I am really concerned about that. Having told you about the dark spots, I don't want you to be attracted to going immediately and looking at the sun. That will be very, very disastrous. But look at the sunspots. They just look so insignificant. They look like some black spots. Now you would say that why should one measure the number of sunspots? There are some dark spots on the sun. They are of no consequence. But I want to show you, this is what a high resolution picture of the sunspot shows. Sorry, this is not very clear. It's very clear on my disk, but you see the lines going through everywhere. Each of these spots, magnetic fields emerge from them. So they are the sources of magnetic lines of force on the sun. So you are again, if you measure the sunspots, number of sunspots on the disk, you are actually looking at the magnetic field of the sun. I hope you are able to see these lines here. And so these are the magnetic lines of force which come out of the sun. Now this is the number of sunspots which have been recorded in the past. Some of these are not reliable at all. So these are all very reliable. Up to here is very reliable. But these are scattered records, and one is not sure about their whether they are complete or not. But 1840 onwards, the record is very good. And so one of the things which you see here is that there is an 11-year cycle which repeats. And if you do an analysis of this record, then you see there are also 22-year cycle. Sun exhibits a 22-year cycle, and also one 88 years Gleisberg cycle. So you cannot see it from here, but you have to analyze, and then you see this sun exhibits so many active cycles. But since the record is very short, you cannot see this cycle visually. So as I said, please remember that the record is only reliable after 1848 or so. So we have very limited good record of these sunspots. So the same thing, some of the records are good in between, and some are questionable. And before the 1700 to 1748, the record is very poor. And this is not my judgment. This is the judgment of people who work in the in the solar cycles. And they have looked at the original records which have been produced, and this is their judgment on this, on the reliability of the sunspot data. So this is again the same picture. So just to remind you that this is very small, we have only less than 200 years of sunspot record. So before that, people try to see the information on aurorae, because when sun is active, then it emits very strong solar wind, and these particles, they are ionized particles, they bombard the polar regions, and you get auroras. So if you don't have aurora during certain period, then you can say that the sun was not very active. And on the reverse side, if you have a lot of aurora, then you can say then the sun is very active. So this is a sort of record, as I said, 1850 to this side, the sunspot record is not very reliable. But by combining sunspots and aurorae and all this, people came to the conclusion that there was a period of about 50 years, 55 years, when there were essentially no sunspots. Now this is a conclusion based on some of the unreliable data and then mixture with the aurora data. And then they say there is a Dalton minimum, but this again, Dalton minimum also falls on the side where we have suspicion on the accuracy of the sunspot numbers. But in the recent periods, you know, there is you can see the sun has a lot of sunspots. So they call it modern maximum. So recently the sun has become a little more active, but the real record which is useful is only this much. This is very famous. Everybody talks about it. They even make the statement that this is a period, 1645 onwards, for 55 years, when sun had no sunspots. And this has become extremely famous. Now we will look at it, whether we can provide some information to you about it. Actually, one of the reasons why, I mean, there are more than one reasons. One of the reasons was to see if solar activity has something to do with climate. And if so, can we correlate these? Now, we don't have enough data today, but more data will come in future, and we will be able to certainly correlate the effect of solar activity on climate. The second thing was, I wanted to know whether in the past Maunder minimum like period happened or not. See, Maunder minimum lasted, according to most studies, for 55 years, and that is 5 solar cycles. And for 5 solar cycles, a sun which exhibits very routinely 11-year cycle, as you have seen in the pictures I have shown you, why there were no sunspots? And I wanted to know whether in the past there were periods when there were essentially no sunspots for long periods of time. So there were two reasons essentially why I wanted to develop a method which can measure solar activity in the past. So the major question is before us, how do we measure solar activity? And just to remind you, solar activity is not the total flux coming out of the sun, but the solar activity is a measure of the magnetic fields which come out of the sun. So the big question before us is, how do we measure solar activity prior to the historical record? And the historical record is only 1850 onwards. So fortunately, we found that there is a good physics background to it, and since sun produces magnetic fields, so it makes some effect on something. And this is the thing which got our attention, and we said that we can measure the past magnetic field of the Earth, the magnetic field of the sun, and therefore we can get the solar activity. And this is what I want to discuss with you now. During a solar eclipse, when you don't see the disk directly, which is very bright, you see a picture of this type, and this is the plasma. This is the plasma atmosphere of the sun. So sun is very active, it produces plasma, and this is what we are trying to measure. Now when cosmic rays enter the heliosphere, heliosphere is the sphere up to where the solar effects are there, and this is the region bounded by the heliosphere is the region bounded by the sun in which it has effect. So when the cosmic rays enter the heliosphere, then the plasma emitted by the sun affects the cosmic ray flux, because charged particles, which is cosmic rays, consist of charged particles, and magnetic fields interact very strongly. So the next figure shows how this effect is produced. Now what we have here is, in the y-axis, which is a logarithmic axis, it is giving the cosmic ray flux in some units. And we don't have to worry about it, but we say that this is the cosmic ray flux, and this is the energy of the particles which we are dealing with. And you can see that during different years, this is 1977, this is 1965, 1970. So this is the period when the number of sunspots we know were very few, and this is the period when sunspots were very large. So you can see the cosmic ray flux is decreased when sun is very active. And this is expected also, because when sun emits more magnetic lines of force, then this modulates the cosmic ray flux. So if we can measure past cosmic ray intensities in the near Earth space, then we can probably measure the solar activity in the past. So this is the clue which we had, and we then proceeded further. Now, this is not an easy task to measure cosmic ray flux in the past, because the cosmic ray flux on the Earth is affected by the geomagnetic field of the Earth, which changes very often. And we do not have a complete record of the geomagnetic field, not accurate record anyway to make corrections. There are meteorological parameters, the winds and rainfall, precipitation, and all these, and there are many parameters which affect the cosmic ray flux. So how to measure? So this was our big task, where to measure the cosmic ray flux, which is dependable and which you can trust in. So it turned out that, as I will convince you in the next slide, it turns out that the best place to measure cosmic ray intensity is in the polar region. And fortunately, in the polar region, ice sheets are there. So since ice sheets accumulate continuously with time, so ice sheets also give you a record of cosmic ray intensity if we can make the ice sheet give us record of cosmic ray intensity. I think many of you have played with a bar magnet, and the bar magnet, if you put the filings, iron filings around it, so they always arrange in this particular pattern. And this is the bar magnet, south pole and north pole, they are symmetric. And the lines of force here go essentially along the bar magnet. Now there is a property of charged particles that if they come in this direction, then the lines of force are perpendicular or at an angle to the magnetic lines of force, to the incident direction of cosmic radiation. So if the cosmic radiation is coming this way, and the Earth also has a bar magnet inside us, it has a dipole field. So the Earth's field is very similar to that what you get from a bar magnet. So if cosmic rays come here, they are very strongly affected, but they are coming at right angles to the lines of force. But if the cosmic rays come along this direction, they are coming along the lines of force, so essentially they are not affected at all. So it turns out, it's very clear that you should measure the cosmic ray flux at this place in the high latitudes, north or south. So we know where to look for it, but what do we look for in the ice? Ice is a very pure substance, but actually from the science point of view, it has lots of properties which you can measure, which are very interesting, which tells you about the past climate, which tells you about the accumulation history of the ice, and as I will show you, it tells you about the solar activity in the past. So when ice accumulates, ice is hydrogen and oxygen, and cosmic rays, when they interact with oxygen, they produce carbon-14. Now this is not the carbon-14 which you find in the atmosphere and the oceans and everything elsewhere. That's the carbon-14 which was discovered by Professor Libby. But this is a carbon-14 which is produced in the ice sheet in situ as the ice accumulates. So the amount of carbon-14 which you produce will be, of course, expected to be proportional to the cosmic ray intensity. So if you can measure the carbon-14 which is produced in the ice, you essentially get the cosmic ray flux. And this will be independent of the geomagnetic field of the Earth, which is very variable, and so we don't want to go anywhere else. We have to go into the ice. So it's very strange that finally, to measure how sun varied in the past, how the solar activity varied in the past, we go and look into the ice sheets. So one of the measurements we did was in the Greenland ice sheet project in the summit Greenland. This was an ice core which was drilled about 10 years ago. And this is not exactly 90 degrees north, but it's very close. So the effect of geomagnetic field is still very, very small. It only affects particles of less than 100 million electron volts. But most of the cosmic ray particles are much higher energies. So although this is not at 90 degrees, but still this is a very good ice sheet to look for past cosmic ray intensity. The Holocene is the last 10,000 years period, and the glacial period is around 15 to 25,000 years ago, when it was very cold. So the accumulation rate of ice is about 20-25 centimeters per year in the warm period, and in the cold period it is about 8 to 15 centimeters per year. So we studied this core and measured carbon-14 as a function of depth. Now I don't want you to go into details of this, but essentially I want to show you the amount of carbon-14 which you will find in the ice is proportional to P0, which is the carbon-14 production rate in the ice. And therefore, since the cosmic ray production rate in the ice is proportional to the cosmic ray flux, so you are essentially, by measuring the carbon-14 in the ice, you are measuring the cosmic ray flux. Now, there is one more problem. As you go farther back in time, the carbon-14 decays. The half-life of carbon-14 is only 5,700 years. And therefore, the amount of carbon-14 which is produced is also decaying. And therefore, you need very large amount of ice. See, normally the people who collect these ice sheets And if you are approved by National Science Foundation for research, they generally give you less than 100 grams of ice, because that is sufficient for measuring carbon isotopes and oxygen isotopes and various things which people do normally. But the requirement for us was minimum of 2 liters, 2 kilograms of ice. And in the old ice sheets, which were 35,000 years old, we wanted about 10 liters or 10 kilograms. So I had to convince them, and we are very fortunate that they agreed with this, and they gave us huge amounts of ice, which made it possible to make these measurements. I don't want you to look at these measurements, but essentially the carbon-14 concentration is very variable, and I want to show you a plot. This is as a function of depth. So here we go up to about 2,200 meters depth in the ice core, but we know the ages. So this is the depth, and as you must have realized that as ice accumulates, the lower layers are made thin, they spread out. So the age is not proportional to the accumulation rate, but the ice thins at the greater depths. So converting it into the age, this is what we get. I want to show you a better picture of this. So this is the information which we got by measuring ice. So essentially, there was a nearly factor of 2 rise in the carbon-14 around 9,000 years ago and around 35,000 years ago. And here there's a nearly a factor of 2 decrease in the carbon-14 production. So this is a period when there were very few sunspots, and here also. And this is the period when the sunspots are very large, which affected the cosmic ray flux. So we were very happy to realize that at least there were 2 periods here in the Greenland when we may have had Maunder minimum type of activity. That sun for 50, 60 years, that is several cycles, 11-year cycles, 5 to 6 solar cycles, the sun was extremely quiet. And there was, of course, a period when sun was very active. I don't want to go into this detail. Essentially, the information which we got is consistent with the tree ring data. But now, after having done that, and when I talked to scientists and they said that, look, you are talking about period where no information is known to anyone. So how do we believe you? So I said, okay, then I will look at the last 1,000 years when historically people think there are many periods of low solar activity, although they are doubtful because we don't have accurate sunspot data in that period. But still, let me try what happened in the last 1,000 years. Okay, so for doing the historical period, at least in the historical books about the solar activity, this is what people say, that there were periods of low solar activity, 4 of them, and this is the period when the sun was not very active, but we don't know how active they were, but they think there were few sunspots. And you will remember, as I have discussed earlier, that reliable sunspot numbers are only after 1845 or so. So this is a period when the historical record is based very largely on aurorae. So it's a combination of sunspots which are not reliable and the information on aurorae, and you put them together and you say that this is the story. And there was one period when sun was very active, and this is the 1100 to 1250 AD. So our task was, after doing the 35,000 year rough record of the events in the last 35,000 years, because we could have measured much more ice, but we haven't done that. But we found 3 periods which were interesting from the solar activity point of view. So now we said, let me look at this. Now this is an acid test because This is a historical period, and I do not know how good the historical period record is, but you will see today, and you can decide whether I am right or the historical period is right. So this is the Aurora record. This is Aurora and this is Aurora, both axes, and this is between 1800 to 1100, and this is the period which is called the Maunder minimum, and this is the period when this is called Dalton minimum. But you know, this is interesting. During a long stretch, very few aurorae were recorded. Now this again, this is not an institute which measures aurorae. It's not something which is done. This is done by people who are interested in seeing aurorae. So it's a sort of private hobby of people. And once again, this information may not be complete. But it still is very remarkable that during this period, number of aurorae are very few. And during Maunder minimum, we had some aurorae. Okay. So we went to the South Pole Station. Now this is a very interesting place because this is exactly 90 degrees south. So it's in the Antarctica, and the altitude is 2800. The reason why we choose a high altitude station is simply this, that we want to be as close to the cosmic ray flux as possible, because when cosmic rays enter the atmosphere, they produce some secondary particles. So it's important to go to as high altitude as possible. Now if you remember, in the Greenland ice sheet project, our accumulation rates were during the Holocene around 20 centimeters per year, but here the accumulation rates are 7.6 centimeters per year. And this is recorded very nicely by oxygen isotopes, and lots of people have done this work. So from this is very reliable. So if we believe the historical record of the 4 minimum which I showed you and 1 solar maximum, and if I assume, because theoretically this is what I expect, when there are no sunspots, the cosmic ray flux will increase by a factor of 2. So based on an expectation of 2x cosmic ray intensity, during Wolf minimum, Sporer minimum, and Maunder minimum, and Dalton minimum, this is the type of carbon-14 concentration we expect in the South Pole ice. And during the solar activity, when it was high, the carbon-14 activity will drop down by a factor of 2. So these are expectations. Let us see the results. So we were limited by the amount of South Pole ice, because much of the South Pole ice was used up. And these are the number of measurements we made, about 15 measurements. And now if I put it on the the expectations, the simulations which we did, this is the picture we get. So you can see that during a period when we expected this much, we got something like this. But during Maunder minimum and Dalton minimum, we are getting a broad maximum. But during solar maximum, the cosmic ray carbon-14 has decreased quite a bit. So now I want to conclude this and show you what we get. So this is the same picture which you just saw, but it is now put on half the page. So we conclude from here that the evidence for solar maximum around 1050 to 1200 is there. So we agree with the historical record here. There could have been a Wolf minimum, but we have only one point in between. So I don't make any statement about this. So we do not have enough data points, and this is the reason why we want to get more solar, more South Pole ice core to work with. Sporer minimum, we have a beautiful agreement, and is consistent with no sunspots or few sunspots during 1450 to 1500. Now, the Maunder minimum, we don't have too many points, but we do see a very broad minimum, not like these, but very broad minimum when solar activity was very low. And it is not agreeing with the Maunder minimum, otherwise this point should have been higher. So we actually are limited by the number of ice points, and therefore we are trying to get a new ice core drilled in the South Pole, and then we will make maybe 30 or 35 measurements and really cover the whole period and really find out what exactly happened in the past. But we are not agreeing just now with the Maunder minimum, but we are getting a very broad minimum, which is not in agreement with the historical record. So what we find is that in the last 32,000 years, there were at least 4 periods when very few sunspots were there on the solar disk. And we find periods when solar activity is high. Now, the new method, we can ask the question, how good is your new method compared to the old method, which is just measuring the number of sunspots? See, the number of sunspots vary in size. So we have no idea what the magnetic field is emerging from the sunspots. So if you just count the number of sunspots, you have some information on the magnetic field, but you don't have a quantitative information. The cosmic ray flux we measure is inversely proportional to the magnetic field produced by the sun. So we are much more accurate. This method of measuring solar activity is much more accurate than the method of measuring number of sunspots. So the new method goes back only up to 40,000 years. The reason is the half-life of carbon-14 is about 5,700 years. So in the game of nuclear physics, in the radiochemistry, we know that if the half-life is, we can only go back to 6 half-lives of the radioactive isotope, because then it's reduced to 1/64 of its value. So then it's very difficult to make these measurements. So in the case of carbon-14, it is generally agreed that you cannot go beyond 40,000 years easily. If there are methods which can be used, but they are very painstaking methods. But you can go back to only 40,000 years. So this new method which I discussed with you today, unfortunately goes back only 40,000 years. The climate record goes back to millions of years. So we need a new idea. And I have been scratching my head, I do not have the idea. But I would like to ask ideas from the audience. If somebody has an idea how to go back to much longer periods, and you don't have to go to the ice, you can do it from somewhere else. But this is a very important thing. And if we do that and measure solar activity in the past, and then compare it with the climatic record, then we will have a very good information on how much effect on the climate the solar activity has. But we know that the total solar flux doesn't have much variation, so that's not the one which is producing the climates. As I said before, that Earth is a very big system consisting of the cryosphere, the oceans, and the lithosphere, and all this, and heat is there in all these systems. A small change in heat somewhere can make a large change in the reservoir, and the heat can come out, or heat can go into the oceans and cause cold periods. So this is very important. We are dealing with a problem which is very simple, that we know it is not the direct energy which coming from the sun which is producing the climates, but there is some sort of feedback in the system somewhere which is disturbing the system to produce warm periods and the cold periods. So this is, you may ask me some questions at the end, but I would also like to ask you this question. Please think about this. We can measure solar activity for much longer periods. To my knowledge, there is no other direct method available to date besides the one which I have presented for measuring the paleo activity of the sun, because we are directly measuring the magnetic flux coming out of the sun. Well, that's all I had to say, and I would be very happy if you have any questions or any discussions following this. But I did mention that you don't have to use ice. Maybe there is some other idea so that you can go back to millions of years. This is the only idea which I tried, so this is not necessarily the only idea.
How can you be sure that the cosmic ray flux is always the same and is being modulated by the plasma rather than having the cosmic ray flux being modulated by something out in space?
You are right. We do not know, but of course, if we are near a supernovae or something, then of course the cosmic ray flux can change very much. But certainly during the last 40,000 years, we didn't have a supernovae close to the solar system. But if you go to a million years, there may be some problem that the cosmic ray flux in the space also changed, in the space near the solar system changed. You are quite right about that, but we are just now assuming that the cosmic ray flux has been constant. Actually, Jim Arnold and I did measure the cosmic ray flux using meteorites, and we came to the conclusion that the cosmic ray flux didn't change very much in the past millions of years. But of course, if you are close to a supernovae, then of course the cosmic ray flux can change very much. Thank you very much for this question. Yes, please.
I know we have a pretty good bunch of data for diatoms and coral and the accretion rates of the calcium based on climatic, dark climatic data. And that obviously builds up in layers. So you're looking for a different way to measure that radiation. If we know the accretion rates based on climate data and whatnot, if that correlates to that graphic representation of the cosmic rays, that might be a key to finding another benefit.
Well, essentially what we are saying is that some of the accumulation rates in the oceans may be related to cosmic ray flux. You are quite right. One has to think. I have not given much thought to it, but we must think about this. This is how we get new ideas. I mean, the new ideas take a little longer to work out. Yes?
The cosmic rays would indicate that it heats the atmosphere, it heats the ocean store heat. Obviously, there's a lag. There's a lag in the heat index of the oceans, but it would still get some sort of ray.
Actually, you are quite right. One of the big things which people have been talking is that cosmic rays, when they enter the atmosphere, they produce ionization. And this changes the levels of clouds formation. And if the cloud formation level is higher, then more of the solar radiation which comes in will be reflected back into space. So there have been at least a dozen papers on this, but no direct agreement no consensus has yet appeared on how cosmic rays affect the climate. But I am sure that this must have a profound influence, but we don't understand yet. More research is needed on that. But you are quite right. We should think about in such directions. Yes. I'm not quite clear about your question, but essentially, if I understand right, your question is, what is the resolution you require when you go farther back in time? Right. And essentially, if we find that there is a gradual change in cosmic ray flux, which we didn't find in our work, and supposing there was a slow change in the cosmic ray flux when you go back in time, then of course we would have measured the one important fact that cosmic ray flux itself has been changing with time. But if we find that there is a baseline just like we had in our data. There is a baseline, and then about a factor of 2 increase takes place, then we can say the cosmic ray flux has been constant in the past. But I think the resolution, we can certainly look at anything which changes more than 30% or so very easily using the ice record. But we must think of other records which will take us farther back in time. But you asked me a difficult question, but I think the answer is that we need to improve, we need to look for different sources where we can find the record of solar activity. Yes, please.
Is there a significant biological contribution to the C14
You are asking me, the question is there a significant effect of change in carbon-14 on the biological activity? Now, you are asking me a very difficult question. We have to learn more about these things here. This is good that you asked me these questions. We will think about it. Yes.
Maybe one more question?
The question is, are there mineralogical changes in the rocks due to changes in the cosmic ray flux? This is again a very important question. These things we will learn in due course of time, but these are the directions in which we have to think in order to develop a new method of measuring solar activity for longer periods in the past. I'm sure there must be important effects of cosmic radiation on the lithosphere, in biological effects, everything. So whatever these questions you are asking me are certainly very important. One has to know more about it, but at present our knowledge is limited in this. Thank you very much for asking that question.
Well, we're about out of time. I want to thank you very much for a wonderful
Thank you.